like it means nothing.
Hi. Today I want to talk about our journey in developing our own C2 framework. So just to start with, who am I? I'm Martin. I'm originally from Munich. I've been living in Norway for some years now, in Oslo. I have about 8 years experience in InfoSec, and for the last 5.5 years I've been working as a penetration tester and red teamer in PwC Norway. You can find me on Blue Sky, you can find me via email, and my main interests in work are testing industrial control systems, Active Directory, internal networks, and also automating annoying tasks and implementing cool tooling. So yeah, this story that I want to tell you today, it begins in 2020, and as you might remember, there was a little thing happening back then. We were at the beginning of the pandemic, and we were supposed to go to on a penetration test of an internal network. The problem was that we couldn't travel anymore, so we had to find a way how to perform the test of internal network remotely. And yeah, so what we then came up with was what we called our remote pen test platform, which is basically just a way to connect into our customer's environment and be able to test from there. And I'm just going to very quickly show the rough design, and because that's going to be a bit of important later why we went this route. So it's a bit complicated, but basically we have a pen test machine that's at the customer. It's more or less a Kali Linux. It is connected via an OpenVPN tunnel to our firewall in our server room. Through that, we have a reverse SSH tunnel through which we then can SSH into the pen test machine. We did this just so we didn't have to open any ports into the network that are accessible on the internet or something on our customer side. And the problem we have here is that this outer OpenVPN tunnel uses UDP, and getting UDP through a corporate firewall can sometimes be a challenge. You have to deal with firewall exceptions and this kind of stuff, and it's a bit of a problem, and we didn't really want our customers to have to make firewall changes just for us. So what we came up with a tool that we called Red Proxy. This was basically a summer project in 2020 that basically just tunnels UDP through HTTPS. And for this, we used a technique called long polling. We'll get back to that in a bit. And yeah, its main goal is basically, again, tunneling UDP through HTTPS, but also that if a firewall or something or a proxy inspects the TLS traffic, meaning it breaks open the tunnel and decrypts it, that even then it still looks like valid HTTP inside. That is important so that we can go out on port 443 and we just look like a normal HTTP application, which is almost always allowed, and we can just go through and nobody's going to bother us. So yeah, this was written in .NET Core 3.1 and basically very shoddy. It was my very first C# project, so the code was quite bad, but it works. Yeah, and here we see what long polling is, just very quickly. Basically, it means the client sends a request to the server just sits on it until it can send data back. Because in HTTP, of course, you have a request and the server can only respond to an existing request. So without a request, the server cannot send unsolicited data. At least that is the way if you don't use fancy stuff like WebSockets, which again might have problems with certain firewalls. So that's what we did there. That's Red Proxy, and that is basically the origin of our C2 framework, even though it doesn't look like it yet. Then, a few months later, at the end of the year, end of 2020, we actually weaponized it in an unexpected way because we were the customer where we actually got code execution on a machine. And the problem was that this customer actually had great internal segmentation. So as a penetration tester, I can tell you that this is sadly something we don't see very often. Because, yeah, great segmentation helps a lot against attackers. And in this case, it just meant we couldn't get a reverse shell back to our machines. We had code execution, but any port we tried towards our machines in the client network, it just wouldn't go through. So we then noticed, however, that we have full outbound internet access, but they were using TLS inspection. And then we realized, wait, we have a tool for that. We have Red Proxy. Problem is, Red Proxy at this point only supported UDP. So what do? Well, Netcat also supports UDP. So we had a UDP reverse shell through Red Proxy and then out via the internet. It worked. Problem was just that it was very unordered, because again, UDP is unordered traffic. So if you get a shell output and every line is like completely out of order, I mean, it works. You can put it back together, but it's not nice. So what we did is we quickly hacked together the already dirty Red Proxy code, added some very quick and dirty order transmission to it to get it to work, and then we had Redcat. And this is basically a screenshot from that engagement where we actually got a shell back on our server. We got a system shell, and we could demonstrate the client that not only had we able to get code execution, but we could also get it out via the internet. And of course, there are other tools out there that support this. So I'm pretty sure Meterpreter from Metasploit, for example, also supports HTTP outbound tunnels. But this was something we could do with our own tools. So that was cool. And this was also the point, basically, that we realized this could be much more than just the UDP tunnel we were doing initially. So we wanted to actually do a bit more with it. And that is basically when we decided, OK, we're going to try to turn this into a C2 framework. And now I just want to very, very quickly explain what a C2 framework is, because if you work as a red teamer, you probably already know it. But many people, I think, might not know what a C2 framework is. Basically, the C2 stands for command and control, and it's also known as a post-exploitation framework. So basically, this is something you use once you already have access on a system. Then you basically start an implant or agent on that machine that connects back to your C2 server, to your command and control server, and you can then do whatever basically on that system. And it comes in various flavors. It's used for persisting your access. You have popped the shell, you want to stay on that machine. And also maybe you want to escalate privileges either locally on that machine, i.e. you want to go from like your service that you compromise to system, to root, to whatever. Or maybe you want to move around in the network, in the Active Directory, become domain admin, and make the local, first escalate privileges in the network. It's often used for penetration testers and red teamers for adversarial emulations, meaning that when we try to actually emulate a threat actor, we will use tools like this because, yeah, that's what they use. They either use the same tools because some of these tools are commercial or open source, or they have their own tools, more advanced adversaries. So state-level adversaries will, of course, have their own tools. So yeah, that's basically that. And there's a bunch of tools out there already, proprietary ones, open source ones. The problem with the ones out there is that they are often already fingerprinted by AV and EDR, so there's static detection for them. There's often also behavioral detection, and that is something that just you have to be aware of when you use these tools, and that basically you need to work around when you use them. So here's just a few examples of them. Cobalt Strike is a well-known one. Root Ratel, those are both examples of proprietary ones. And there's also, for example, Covenant or POSH-C2 as open source ones. So yeah, now that we decided to make our own frame as a C2 framework, we ended up calling it Citadel. It is basically PwC Norway's in-house C2. We've been developing it since 2020. And it's still written in C#. We are now at about 350,000 lines of code, so it has grown quite a bit. It's compiling, targeting various different versions of .NET Framework and the more modern .NET that Microsoft released. And basically, because we're targeting .NET Framework 3.5 at the lowest, it will run on any Windows starting from Windows XP Service Pack 2, but also Linux and macOS. And it also nowadays runs on ARM64 Linux embedded devices. So we've had our implants running on embedded devices a few times, and that just works. It also has a bunch of built-in features. So we have tunneling, TCP, UDP tunneling, SOX5 proxy. We have Unix sockets. We also have WebSocket support. We can, of course, interact with the file system, the registry. We can browse SFTP shares. We have various process injection, command execution features, both locally as well as across the network. We can take screenshots. We can interact more closely with the UI via VNC. And we have various Kerberos operations, Kerber roasting, injecting, dumping Kerberos tickets, whatever. Yep. We have assembly side loading. We have support for beacon object files, and lots more. And also, we support various communication channels, basically how the agents communicate with our server. The most common one, I guess, is HTTP, HTTPS. For that, we have domain fronting and malleable profile support. We have WebSockets, TCP, name pipes, file shares, Gmail drafts, and also we have the ability to add lots of more stuff whenever needed on a very short notice. Now I want to talk a bit about the architecture we chose. We thought quite a bit of how we want to do this because we wanted to make it extendable and easy to use, and so it's easy to add new features. So basically, we looked at how networks normally work. So for those of you that are a bit more familiar with network technology, you have probably heard of the ISO-OC model. It's basically 7 layers, and each layer provides services for the ones above it. So the lowest layer is the physical layer. In the real world, this would be like your fiber cable, the Wi-Fi medium, whatever. And in our case, that would be whatever protocol we are using, so HTTP, SMB, whatever. Then we have the data link layer. On our layer there, we have the connectors. So every instance of our C2 framework, be that server or implant, has at least one connector, or potentially more. We'll come to that later. Then above that, where the network layer would be, so the layer where normally IP, the internet protocol, is, and where routing happens, there we have our multiplexer, which basically just routes information between different things, different components. And then above that, that would be the transport layer and all the above layers. There we have our applications. And applications in our context in Citadel are basically the features we have. So there's applications for SOCs, for Kerberos, for DCOM, for anything that we do, it's basically an application. And the way we do it is that we have an application on each end. So for every application that runs as an application in our implant, we have exactly one application on this side on the server. And these two applications exchange data, and that's how they communicate. And because we have designed it in this way, now if you want to implement a new application, you don't have to worry about how you're going to get the data to the other side. That is not your job. You just say to the multiplexer, hey, I have data, please take care of it. Same thing with connectors. If you want to implement a new connector, you just take data, send it over, best effort. If it gets there, great. If it doesn't get there, not your problem. You don't have to implement reliability. That's implemented elsewhere. And that makes it really easy to just work on a small feature and not have to worry about the other ones. Now, reliable communication. Because initially we only had UDP tunnels, and then we needed reliable communication. And we thought initially, well, how hard can it be? How hard is it to actually implement this stuff? And turns out it can actually be a bit hard. Because, first you have only unreliable communication, or UDP tunnel, and then we add like a simple retransmission mechanism without congestion control. Congestion control is basically a mechanism so that you do not overwhelm the network with retransmissions, because they can make congestion worse. You don't really need that in this small use case. We thought, like, right, we don't need that, right? Spoiler alert, yes, you do. If you actually want to put some more serious data amounts through it, you need congestion control. So here you see the sawtooth pattern in TCP, courtesy of Wikipedia, that basically explains how it works. Like, it's basically just like this, very high level. It detects when there are too much packets are getting lost, and then it doesn't send that much anymore and slows down. That's on a very, very high level. That is how it works. So basically, we implemented the TCP cubic algorithm, which is the congestion control algorithm used by the Linux kernel and maybe also by other operating systems. And yeah, that was something we implemented like a year ago after we realized we absolutely need that. Next thing we thought, after we had that, now we want to also tunnel traffic that's not just UDP. So tunneling traffic is really easy, we thought. It's just data in, data out. How hard can it be? And you notice the pattern here. How hard can it be? We thought that it's actually oftentimes much harder than you think. Because with like the connection-oriented protocols like TCP, you have to actually keep track of connections. And the hardest thing that we experienced here was actually keeping track of when connections ended and how they ended. Because you can see here, TCP connections can be closed in one way. So first one side says, OK, I'm done with sending. That's when it sends a FIN packet. And then later, which can be significantly later, the other side might say, oh, I'm also done now. So fin on one direction, fin in the other direction. And sometimes you have the RST, the reset, where the connection is closed uncleanly. And getting that to work properly in every single case was actually quite a challenge. And when this didn't work and we had problems in our code, this led to fun issues such as tons of error messages, or applications trying to use dead tunnels. So we were in a red team engagement once. We had a SOX tunnel open and configured Firefox to use that SOX tunnel. And suddenly it would just hang. Nothing would happen for minutes at a time. It would just hang. And the reason for that was that Firefox was trying to use a connection which looked like it was still open to Firefox. Problem was it wasn't actually. Nobody told Firefox about that. And so it kept on trying to reuse these dead tunnels, which of course didn't work. And then another time we had too many open file handles, so we got a nice error message in Linux, more than 1,024 open files. And please stop doing whatever you're doing, basically. Of course, we can increase this limit. This is a soft limit, but if you increase this enough, it actually becomes a problem. So we had to go back to like the debugging and debug this, and yeah. So in the end, we actually spent debugging like I think an entire week on it, cleaning up the code. It was really, really messy code at that time, and just stripped everything out, wrote it from scratch, basically that component, and got it to work. And actually, in the end, it worked quite well. And that's now something we can actually use with very good performance. So, and talking about performance, I just want to like very briefly show what kind of performance we can get through SOX. SOX is probably the most feature of every C2 framework because you want to use a random tool, you just tunnel it through SOX. And to test this, basically, we used a recent version of Firefox and Google Speed Test. And the setup was like such. We had a C2 implant that was sitting in a lab network in Norway. It was communicating with a Citadel server instance that was in the Netherlands in GCP's Europe West 4 zone. And our operator that was testing was, again, in Norway. It was using an SSH tunnel to get to the Citadel server to then use the SOX tunnel that starts there. And both the implant and the operator were on 1 gigabit connections, and Google probably on like a much better connection since it's in a data center. So yeah, first with the HTTPS connector, we got 40 megabits per second upload and 70 megabits per second download. So that is good. You can stream through that. Ignore what it says for latency there. I don't know how Google measures that, but that is not the actual latency. It's worse. So you can stream through it. You can stream YouTube in full HD or ultra high HD. You can watch Netflix. I know it because I tried it. I wouldn't game through it, at least not Counter-Strike or something, because your ping is going to be horrible. When we go to our WebSocket connector, which is quite a bit more performant, we actually get some really decent speeds to that. So that's 120 megabits down and 100 megabits up. So basically, yeah, you can get anything through these tunnels. It will just work. And that is something that was really, really powerful in our engagements. Also, because we implemented everything, so it's abstractly implemented, so using lots of base classes, it was incredibly easy to add Unix socket support. And this was especially interesting because we've, over the last 2 years, had lots of tests of Linux systems where Docker was being used. So we wanted to actually tunnel the Docker socket because on Linux, by default, it's a Unix socket that you connect to issue the Docker commands. So we want to be able to forward that from the machine where our implant is on to our C2 server. So the one side of the application was about 40 lines of code. The other side was like 50 to 60. So all in all, just adding support for Unix socket was less than 100 lines of code. And that was just beautiful, adding that and seeing that it was that easy, because I thought it was going to take me 2 days, and when it took me like half a day. So yeah. I already talked a bit about the different connector implementations. So again, connectors is basically those that provide us with the connectivity. And there we have various classes. We have the request response type connectors. So that's basically anything where a server cannot respond unless it has a request to respond to. So it's not full duplex communication. And there, of course, we have HTTP, HTTPS, we have DNS, and we have ICMP. And then we have the second class, which is the stream connector, basically where we have full duplex connectivity in both ways, meaning the server can send unsolicited data, which makes communication much more performance, of course. We have the raw TCP sockets, we have web sockets, and we have SMP named pipe support, because that one is actually really important in Windows networks, because that's how you can stealthily exchange data inside an internal network with other implants. Then we also have connectors for anything that looks like a directory. So for example, if you have a file share that two sides can write to, then you can indirectly through that have a communication channel over a file share. And we also are able to communicate over Gmail drafts. So both sides connect to the same Gmail inbox and just create draft emails there. And that's basically a directory, and we can communicate over that. So you can imagine if you're in a company that uses Gmail, that traffic will probably not stand out so much in the firewall, because, I mean, it's something connecting to Gmail. That happens. Yeah. And lastly, we have the two files connector, which is basically a specialized version of the file share connector. Instead of creating more or less unlimited files or like a lot of files in parallel, it only communicates via two files, which limits the amount of file creation, file deletion events, and that way might be stealthier in certain situations. So yeah, then also I already hinted a bit at it. What do you do when like some machines that you want to control don't have internet? So first, the default case, you have a machine, for example, a web server in the DMZ, very close to the internet, has full outbound internet access, that can just communicate with the Citadel server directly. All is good, all is simple. You can have your command runner on this thing, and it just communicates via HTTP. It gets more complicated when you maybe want to implant a domain controller that doesn't have internet access. But there we have the ability to relay traffic. And in this case, on the left, you would have basically the domain controller, the DC, without internet access. And instead of communicating directly with the Citadel server, our C2 server in the internet, which it cannot, it would communicate with another implant, for example, our implant in the DMZ, and just communicate via it. The traffic would go only up into the multiplexer and then back down again, and just then go directly back to the Citadel server. And in here we would, for example, like mentioned earlier, use SMB name pipes, because that just happens in Windows land, that you communicate with that over SMB. Now, one thing that you also often see is difference between staged and unstaged implants. The simplest is probably the unstaged implant. That basically means as soon as the code is running, it will have everything that it needs to. So it might be, for example, an exe file that contains all the code necessary. You just drop that on the system, double-click it, and it runs. Nothing, no staging process necessary, it just works. You might not always want to do that, because first of all, it's bigger. Second of all, you're giving the defenders, the blue team, everything about your implant, all the code on disk, nice and easy to use. So that is something that very often you want to avoid. So what is generally done there, and that is not just for us, that is like in very many C2 frameworks, I think basically anyone does this, is that you first have a stager, and that stager requests a payload from the C2 framework, C2 server. And then once it gets this payload, it turns into the full implant. This gen has all the code necessary to communicate. So the stager, in our case, is very small. It's 9, 10 kilobytes, depending on exactly how it's configured. And once it receives the actual payload, it can turn into a fully staged implant. And then oftentimes you have the problem that you do not want these things to end up in a sandbox. Because once you end up in a sandbox and give it like the full payload immediately, well, the blue team now has everything they need to like take apart your implant, figure out exactly how it works, figure out how to block it, how to detect it. You do not want that. So what is often done is that there's like sandbox detection built in and stuff like that. And that itself can look fishy already, because the detection mechanisms can actually get you caught. So what we did is something a bit different. We have a so-called stager lobby. So whenever a stager connects, it has to manually be approved by an operator, meaning it comes in and then we see it, okay, here's a new stager coming in. It gives us some information about the environment it's running in, like what type of operating system it is, what's the host name, what's the username, what's the process name, all these things. And with that information, you can very often already tell if it is inside a sandbox or on the target machine. And once we have approved it, it will go through and get its payload and work as expected. We also have the ability to stage through different connectors, meaning you can stage through HTTP, of course, but also via SMB name pipes or TCP or basically almost everything we have. But also we, of course, have the ability to stage through another implant that is relaying, because again, if you have the domain controller case that cannot communicate with the internet, if you need to stage, you need to be able to stage from another implant as well. Otherwise, you have to use unstaged implants, which we really, really try to avoid. So yeah, that is that. And we had a fun issue once that actually caused every other staging process to crash. Like, the implant wouldn't stage. It would download the payload, and then it would just crash. And it was exactly every second one that would work. So not just like statistically 50%, no, it was every second one. And that was basically caused by a bug where we would decrypt our staging payload on a relaying implant because it was obfuscated with a XOR obfuscation key. And because we did it in the wrong way, the copy, which was supposed to be unchanged in memory, the raw copy, got decrypted in memory, which it wasn't supposed to be. And then like we were standing it basically once encrypted and once unencrypted. And the stager would always try to decrypt it. So half the time it would work, other half would not. And that was a fun debugging process, figuring that out. I can tell you that much. So yeah, and here you just see a quick staging process. So you can see first in the lobby that there's something in lobby waiting, and then afterwards we give the lobby allow command, and then it turns into a full-blown stager. And we can also see much more information about the user. In this case, the user is called Dominic, and the process name, and internal IP addresses, and so on. So at the end there, it's a full-blown implant. Now, since we have connectors over insecure channels, we also had to worry about data protection because we are sending quite sensitive data through this. For example, if we have compromised a domain administrator account, credentials for that user might go through our framework. If this goes over an HTTPS connector, it's probably fine because HTTPS is secure. If it goes over a raw TCP connector, not so much. So we had to add end-to-end encryption. And because of the way we architected this, we couldn't really rely on the default implementations of cryptography that you would normally use. So we did the one thing that basically everybody in IT security tells you not to do. We implemented our own encryption. Because basically we couldn't see a way around, because at this point we didn't have a nice, reliable communication stream, so we had to deal with the fact that packets will get lost, so you cannot just use normal TLS inside the thing somewhere. But because we, of course, know that you really shouldn't do this, like really you shouldn't do this, we basically followed TLS 1.2 as close as possible. So if you are a bit familiar with the TLS handshake, this will probably look similar to you. It's a bit different because of some simplifications we have done, because we don't need to support different crypto algorithms and stuff. Basically, what we're doing is a 4096-bit RSA handshake. We have client and server randoms to protect the handshake against relaying on either side. They are just randomly generated each time. We have a 48-byte pre-master secret, which is randomly generated by the agent and sent encrypted with the RSA key to the server. And then once the handshake is done, we are using the CHA-20 poly 1305 algorithm for our symmetric cipher. And there, because that algorithm needs nonces, and nonce stands for number used once, and it actually, in this kind of algorithm, it needs to be only used once. As soon as you use it more than one time, basically you're screwed, your entire cryptography falls apart. So in order to not have that ever happen to us, we decided to split this nonce into two parts, so that if one part fails, the other one still hopefully protects us. So we have a 64-bit counter that just increases with every packet that's being sent. And then we also, the last 32-bit of the nonce, we just have a securely random generated value. Just so, again, as I said, so that if something were to go wrong, we have the other part of the nonce that's hopefully going to save us. And yeah, for the key derivation function, we basically use more or less the TLS one, different label and different HMAC algorithm. I think TLS 1.2 uses HMAC SHA-256. We bumped that up to 384. And yeah, Basically, it looks like this. Server sends server ID, client ID, server random, and certificate to the agent. Agent sends its information back together with the encrypted pre-master secret. Both sides extract the pre-master secret, and then afterwards generate the master secret from that. And then each side generates the session keys, which are then used to encrypt the actual communication. And yeah, so disadvantages, we have, first one is that we have quite good security even in older .NET framework versions, because you can imagine .NET Framework 3.5 is from the Windows XP days. Back then we didn't have cool algorithms like cha-cha-20 because it didn't exist back then. So we actually had to implement it ourselves, which again is something you shouldn't do, but I'll get to that in a second. Means we still have good security there. We have an authenticated encryption scheme, which again is the cha-cha-20 poly 1305 algorithm. And that basically means that you do not have to worry about whether you MAC first and encrypt then, or encrypt and then MAC, because that's where a lot of the issues in TLS come from. And also we have a low risk of side channel attacks, because even though this is a more or less like non-audited implementation of cha-cha-20, and these usually, it's very easy to implement side channel attacks, but this algorithm was designed in such a way by the people that came up with it, so that it's easy to implement without shooting yourself in the foot by creating side channel attacks. So that's also one of the reasons we chose this, because we actually felt comfortable having that thing in there, because implementing AES, I wouldn't dare, because I'm not a cryptographer, I'm not a cryptography implementer. That is, and I know that in AES it's very, very easy to do that, to implement side channel attacks accidentally. And yeah, also cha-cha-20 is incredibly efficient, even if you implement it only in software, which we have here. So that makes it very efficient and not very resource hungry once the handshake is done. There are some disadvantages with the scheme. The first one is that after the handshake is done and we are in the symmetric encryption, it technically does not provide any replay protection. But in our case, actually, we've analyzed this. It doesn't really matter because of the sequence numbers that we use on the higher levels above the encryption. Any replay of a package that was there before wouldn't really cause any issues, because it would be treated as like a retransmission that would either be ignored or just throw a warning message. So there is not really anything you can do by just replaying these packets, and we have replay protection in the handshake. And the other thing we do not have is perfect forward secrecy, because we don't use Diffie-Hellman. And that only really matters once your private key gets compromised, which we protect against in other ways. And also, these are short-lived private keys that we generate for every single engagement. So the risk there is quite low, and implementing efficient Diffie-Hellman key exchange for old .NET is something we did not really want to do for a number of reasons. So yeah, that's basically how we ensure the security. Now a bit more on the more high-level features. We have a credential manager. Basically, it's a central credential store on our Citadel C2 server. We automatically ingest extracted Kerberos tickets, as well as if we dump LSAS, for example, we extract all the passwords, the password hashes, and put them in there automatically as well. And then we can just use them afterwards in commands we run on the agents. And here we also have it implemented in such a way that whenever an agent wants to use a credential, because, for example, it was told to use it in a command, it actually needs to be pre-approved by an operator explicitly. So an agent that might have gone rogue, maybe a blue team that's trying to figure out which credential we actually have compromised, it cannot just request random credentials. We don't allow that. It has to be explicitly approved. And also, while they are on the agents and not actively used, then we store them encrypted in the memory, just so that by a simple memory dump, you cannot immediately tell what kind of credentials or which credentials we have leaked. Because again, that would give a blue team a lot of information. They see, oh yeah, they have compromised this user, let's just block this user everywhere. And then we lose our access, so that's something we try to avoid with that. And also the last thing, every access is audited. That's just something that we do for ourselves, so we can see, okay, this credential has been used at these times, just in case the blue team ever asks what we did, and also just so we can keep ourselves accountable, that we don't just go willy-nilly with this. And yeah, here you can see a screenshot, basically the end of a Kerberos ticket dump, and then how it is all ingested automatically in the credential store. That is a very convenient feature for us to have to just, yeah, get this automatically done. The next thing I want to talk about is the in-memory invocation of assemblies. So basically, oftentimes you want to run some other tool, because Citadel supports a lot of features, but doesn't support everything. And every so often, you just want to run a C# tool, like Rubius, Sharphound, Certify. We use them all the time in engagements. And yeah, you could, of course, just spawn a new process and just run it that way. But usually, you really do not want to do this because spawning new processes stands out. It generates events. So that's something we try to avoid. And what we do instead is with C# binaries, we can just load them into memory, because again, we are a C# process ourselves. We can just assembly load them, and then it's nice and in there. The problem is, how do you get rid of them again once you're done with them? Because you don't want like 50 different C# binaries in your process just hanging out there. So what we do there is that we create a new app domain. So app domain is basically a concept that's used in the common language runtime. So the CLR is basically, if you start a C# or other application that's in .NET, it runs inside the common language runtime, which is in the process. And there you normally have the default app domain where your program is running in. In our case, this is our Citadel agent with all the different assemblies. And assembly here just basically means an exe file or a DLL. So there's usually multiple assemblies in every domain. And what we do here is we create a separate domain in which we then load the tool, for example, Sharphound with all its assemblies. We run it, we get the output, and once we're done with it, we just unload it again, and it's almost as if it never was there. It may sound simple how to do this, but actually it's a bit of a challenge because also it's different. Because .NET is not .NET. You have the old .NET framework, which is basically Windows only, more or less, and then you have the newer .NET, which runs everywhere. And in the newer .NET, there are nice convenience functions to do this, and you can just do it. It's a bit simpler. In the old .NET framework, it's a bit more tricky. So what we had to do there is we had to drop a DLL on disk that we then could load into the new app domain, and that would then load the binary we actually want to load. So that's something that's not 100% stealthy, because again, we have to drop a small DLL on disk, but we couldn't figure out another way around this yet. So if you have an idea, come up to us, talk to us about it. We would love to know it. We haven't figured it out yet. Maybe it's possible, maybe it's not. So yeah, that's basically the app domain loader. Then also I mentioned it briefly already, the BOFs, the beacon object files. That's another way of extending your functionality, and that comes basically from Cobalt Strike. So the implants in Cobalt Strike, they're called beacons, and the beacon object files is basically a binary, an unlinked binary that is compiled in such a way to interact with beacons' internal APIs. And that is native unmanaged code, so not CLR, not C# code. So we cannot easily directly load it into our process because it's different code, basically. But there's tons of useful tooling available for this. So one example is TrustedSec's environmental awareness toolkit tools and stuff like this. And you basically, if you can have this in your C2 framework, you're going to make it so much more powerful because so many awesome tools are available in the form of BOFs. So basically what we did is we had to implement a loader that loads this into our process, hooks it up with all the callbacks and all the APIs. We had to basically re-implement them, emulate them, and then make it work together with our managed C# code inside the CLR. So we managed to do that. We also implement an automatic obfuscation because some of the APIs that are being called have or actually many of the APIs, they all have the prefix beacon and then the feature. And that, of course, if you do like static memory analysis and just see beacon something, bunch of functions like that in there, that's going to stand out to an EDR. That's how you might get caught. So we basically obfuscate these on the fly when they're loaded, just so we don't have that. We also support the BOF pack argument packing. That's a bit more of a detailed thing. And yeah, we also unload them again after execution. So you load the thingy, it does its thing, and then it gets unloaded afterwards, just so we don't leave so many traces again in memory, because yeah, we don't want to leave traces. Yeah, and here is just a quick example of us executing the ADCS, an ADCS scanner BOF file that just demonstrates, yes, we can do this and it works. And yeah, we were quite happy with that because that gave us so much more opportunities to actually do stuff. Also from Cobalt Strike come malleable profiles. Malleable profiles are basically a way of like configuring beacon implants again to like behave differently. What we are using them for is basically so that we can change the way our HTTP traffic looks like. So we can define, okay, you're going to request these URIs with these headers and so on. I'm not going to talk too much about it because we are slowly running out of time here. Basically, yeah, we can change how our communication looks by using them, and that's basically it. If you want to learn more about it, come find me afterwards at the bar. Also, we obfuscate our implants. Basically, we use D-invoke instead of P-invoke, and basically P-invoke is, platform invoke is Microsoft's way of calling native API functions, Win32 or also Linux functions from C# land, and D-invoke is basically a way of dynamically doing that, because when you use P-invoke, the platform invoke, it will basically put it into the import table of your module, and if you include all the LSA, connect, untrust, and all the cool fancy functions in there, EDRs will look at you very, very funnily, and with D-invoke you can hide that much more, because you can just manually scan the memory for the DLL and then find the thing. That's a technique that has been around for a few years now, and we're using that as well. We're also trying to not have large byte arrays that are fingerprintable in there, because you can imagine if you have like a 16-byte string in there that's like always the same and nowhere else, well, that's going to be a very easy detection to write for a security engineer. So we try to avoid those as well. And we also have a self-written tool that's based on Roslyn that's running before builds that renames functions, classes, properties, obfuscates string contents, and does various other changes. Because again, this is C# code is similar to Java. If you ever decompiled it, you get quite a bit of like function names and class names back. So in here you can just very quickly see actually a D-invoke function where the function name is changed, the strings are obfuscated, and also instead of like saying what function we're calling, we are just saying, okay, here's the hash of this function, that's the function we want. And basically, this is still a work in progress. We are not doing anything near to what is possible yet. We obfuscate more as it becomes necessary. So we've had like a few incidents where we started getting detected, got some static detection rules, and then we just like changed stuff around a bit, improved the obfuscation, and then we don't get caught anymore. And so far, that's been working really well for us. One thing I just want to briefly mention is that we have a script engine. We call it Catalyst. It's based on Lua. It's possible to listen for different events like agent connected, application started or stopped, and so on. Can do anything an operator can do. We basically use it for integration testing. So whenever somebody pushes to our Git repository, we run unit tests, and we also run integration tests just to make sure we don't break stuff. And we had some fun issues with that. I sadly do not have the time to go into this now, but again, if you're interested, talk to me afterwards. Yep, we also have a really cool nifty feature which basically allows us to quickly run code via tunnel, because C2 operators or like any red team operators, we are all lazy people, we just want stuff to work. That's why we don't fiddle around with manual shells, reverse shells, because yeah, it's tedious work. So we implemented a way where we can basically create a SOX shell, which is basically a pseudo shell that automatically tunnels every command you enter through the SOX tunnel you have set up. So if you have stuff like the impacket tool, for here, for example, the get user SPN impacket tool, which basically just does Kerberos roasting. If you enter the SOX5 shell, any command you enter there will run on the operating system of the underlying machine, but will get prefixed by the proxy chains command with the correct config file. So it will just transparently for you run it through a proxy, which is really convenient for stuff like impacket when you don't want to think about, okay, I just want to run this tool. I want the network or all the network traffic to go out on the implant, and that just works. That's really, really cool to use. And now one of the last things I want to talk about is our deployment in practice, because a C2 server by itself is powerful, but we have lots of supporting tools around this. So basically, for deployment, we use Jenkins together with Ansible scripts, and we also have a bunch of supporting tooling, like I said. And one of them, the one that's probably most relevant here, is the small self-written tool we call VT Hash Checker. There are other tools like this out there also on GitHub and stuff. Basically, we take a hash of every file that at one point runs on an agent, and then we periodically check these hashes against virus total. So if a blue team ever sees one of our implants or any binary we drop and wants to know, okay, is this malware? This looks fishy, and they upload it to virus total, we will within minutes get a ping back and get notified, hey, somebody uploaded a file with your hash up there, and that's how we then immediately know. As you can see here, a notification we got in the chat then, somebody uploaded the file. This was actually the ADCS enum BOF file here, and you might want to know about this. So we can then react if this happens, which is really cool because it gives you some heads up when the blue team is getting close to you. So yeah, and now I just want to wrap up with some final thoughts basically about this journey. And first thing is basically that writing your own C2 framework is surprisingly fun. You end up learning a lot while doing it about how networking works, network protocols, how the attack methods work under the hood, and also about OS internals. Sometimes you learn stuff you don't want to know, and I learned lots of stuff I didn't want to know and stuff I still regret knowing, but stuff didn't work and just had to figure it out, and you spend days upon days on it, and yep, in the end you learn stuff, and that is saddened sometimes. But yeah, it takes a lot of resources to build. We invested ungodly amounts of hours, lots of weekends, lots of overtime, and yeah. But the cool thing is, first of all, you can easily add new features or fix bugs as needed during engagement. That's something you can very quickly do. And most of all, you can have the ability to emulate even advanced adversaries, because that they don't have your normal Cobalt Strike or something that you can buy off the shelf. They have their own custom tooling like we have that doesn't have static detections immediately. So yeah, that's basically that. There's lots of more stuff I could talk about, which I sadly do not have the time for because I could talk about this for hours. So feel free to reach out to me or to any of my colleagues. This has been an effort by our entire team, and yeah, find me at the bar, send me an email, hit me up on Blue Sky. Yeah, and thank you for your attention.